Welcome everyone to this week's edition of the Extracellular Vesicle Club. So today we have a couple of special guests, and our presenter is going to be Amandine Bonifay. She's been working at the Center for Cardiovascular and Nutrition Research in Marseille, France, and she's working with somebody whose name I've known for a very long time, Romaric Lacroix. So I remember that when I was getting very interested in EVs and their standardization, that there were some very key papers that had been published by Romaric and his co-worker, Françoise Dignan-Georges. And so Romaric has his own laboratory now and has been supervising Amandine. And we're going to hear about some of the very exciting work from their group that was recently published in the Journal of Extracellular Vesicles. So Amandine, you shared your screen here, and we're all looking forward to your presentation on counting and sorting neutrophil-derived EVs. So please go ahead, and thank you for joining today.
So thank you for this kind introduction, and hello everybody. First of all, I would like to thank the EV Club for giving me the opportunity to present this work, so published this year in the Journal of Extracellular Vesicles. I will present you a new strategy to count and sort neutrophil extracellular vesicles that we applied in infectious disorders. As you know, the term EV includes different subsets of vesicles. It exists a wide variety of EV in terms of size and formation mechanisms. Furthermore, cellular origin greatly impacts the diversity of EV. Thereby, EV are involved in many pathophysiological processes thanks to the proteins, lipids, and nucleic acids that they convey, and may have an interest as a biomarker. Among circulating EV, neutrophil-derived extracellular vesicles are largely studied in the literature. NGEV are contained in several biological samples like plasma, but also sputum and atherosclerotic plaque. NGEV are involved in many diseases like infectious, cardiovascular, and inflammatory diseases. Several studies show a link between the level of NGEV in plasma and the outcome. For example, the increase of NGEV in plasma is correlated to mortality during infectious endocarditis and familial hypercholesterolemia. Also, their enumeration is correlated with the disease severity in chronic obstructive pulmonary disease. Moreover, we recently showed that neutrophil-derived EVs support fibrinolytic activity and that their injection in a murine model of septic shock reduced clot formation. Injection of fibrinolytic NGEV modified the hemostatic balance toward a more fibrinolytic profile without impacting the procoagulant activity. This data may suggest a new protective mechanism where NGEV with high plasmin generation capacity efficiently activate plasminogen into plasmin and convey a fibrinolytic activity able to lyse a thrombus. In septic patients, this activity could represent a protective mechanism favoring microthrombi dissolution and organ perfusion, and thereby improving the septic shock outcome. From literature, a large panel of markers are used to detect NGEV by flow cytometry. The most employed marker is CD66B. And so we can observe that the detection of NGEV by flow cytometry is not harmonized between laboratories. Moreover, NGEV identification by flow cytometry remains complex. First, even if neutrophils are largely distributed into the circulation, NGEV represent a rare population among total circulating EV. As they are small events, they have a low antigen density, and generally the staining of EV is weak in flow cytometry. Furthermore, a few neutrophil markers are known for their detection, and they are often selected empirically according to their antigenic expression on the parental cells. In parallel with this vesicular aspect, we have to consider the instrument sensitivity. Over the past year, despite the improvement of scatter and fluorescent parameters, the detection of EV by flow cytometry remains low. Moreover, the high background noise present when we analyze in EV settings led to a partial detection of NGEV by flow cytometry. So, the goal of this study is to improve NGV detection in plasma samples using a new combined strategy, enhancing the flow cytometry fluorescent signal. So first, we produce purified NGV using fresh whole blood, and the neutrophils were collected using density gradient and immunomagnetic separation. Neutrophils were then incubated for 24 hours with media supplemented or not with FMLP for stimulated condition. We collected the supernatant, and after serial centrifugation to exclude cells and debris, we purified EV using ultrafiltration process to concentrate them and size exclusion chromatography to remove soluble proteins. 3 NGV batches from 3 different LC donors were prepared and stored at -18 degrees. According to the MyZev 2018, NGVs were characterized as EV structures using several methods. First, the presence of a bilayer phospholipid membrane enclosed EV was demonstrated by transmission electronic microscopy and by a significant reduction in annexin 5 staining EV counts in flow cytometry after triton lysis and 0.1 micrometer filtration. Moreover, the presence of integrin subunit beta-3 and GAPDH was revealed by Western blot without major contamination by soluble molecules like albumin. Finally, TRPS assay showed that vesicles had a median size of 191 nanometer. So taken together, the structural, molecular, and side features of NGV preparations were in accordance with the definition of EV. So now to increase NGV detection by flow cytometry, we studied 3 different methodological improvements. The first strategy is to select the best specificities to detect NGV. So we realized a large antibody screening on NGV derived from basal or stimulated neutrophils. 54 antibodies with PE fluorochrome were tested, and we analyzed the percentage of double positive NGV, so the number of annexin 5 plus antibody plus NGV among the total number of annexin 5 plus events. The results were displayed as a heat map from 0 in dark blue to 100% in red. And we considered an antibody as positive on NGV at least 15% of double positive NGV detected. So based on 54 antigenic specificities known to be expressed on leukocytes, a large phenotypic characterization of NGV was performed. And strikingly, among the 54 tested specificities, only 15 were classified as positive on NGV, with a significant detection above a threshold of 15%. We can observe that CD15 is the most expressed marker, and we don't find any statistical difference between NGV derived from basal and stimulated neutrophils. Then, to assess the specificity of the selected marker, we tested this 50 antibody expression on the other subpopulation of leukocyte-derived extracellular vesicles, so the monocyte and the 4th subset of lymphocytes. And combining the sensitivity and the specificity performances, 3 antibodies were identified as well expressed and specific for the detection of NGEV. So CD15, CD66B, and CD66C. So then, having a selective antigenic signature of NGV, we next investigate whether NGV detection could be improved by reduce the fluorescent background noise. So we tested to remove 3 antibody remaining after staining the size exclusion chromatography process. In fact, during the labeling of EV, all the antibody is not bound on EV. They are aggregates and unbound antibody, which increase the fluorescent background noise. So regarding the antibody tested, and as illustrated on the representing NGEV labeled with annexin 5 and the 3 selected antibodies, we can see a decrease of P fluorescent background noise, and we can acquire previously undetectable double positive NGEV, weakly stain corresponding to the blue dots. So in conclusion, this washing step allows the median fluorescence intensity of the double negative events corresponding to the background noise and increase the number of annexin 5 plus antibody NGEV detected. Then the third strategy aims to increase the absolute fluorescent signal of NGEV using the 3 selected antibodies, so CD15 and CD66B and CD66C, coupled with the same fluorochrome, phycoerythrin, combined as a cocktail. So to that aim, NGEV staining was compared after labeling with the CD15 alone, which is the best individual marker, versus different antibody mixes composed of 2 or 3 antibodies and with or without a size exclusion chromatography washing. When the 3 antibody cocktail was used without a size exclusion chromatography washing, the median fluorescence intensity of NGEV significantly increased compared to the staining with the CD15 alone. However, we can observe that the fluorescence of the background noise was significantly increased also, and consequently, the separation index between NGEV and the background noise was not significantly improved. And finally, the percentage of NGEV detection was significantly decreased. In contrast, when the 3 antibodies combination was used with size exclusion chromatography washing, the median fluorescence intensity of NGEV significantly increased compared to CD15 alone, and without an increase in the fluorescent background noise. Consequently, the separation index between NGEV and the background noise was significantly increased, and the percentage of detection of NGEV was also significantly increased. We also observed that the staining optimization was less efficient when combining only 2 antibodies for NGEV labeling, resulting in a lower separation index and a percentage double positive NGEV. So the use of size exclusion chromatography washing after labeling drives to decrease the P fluorescent background noise and allows to increase the detection of NGEV. So then we combine the 3 methodological improvements to try to enhance the detection of circulating NGEV from sepsis patients. NGEV in sepsis condition were described in the literature as a potential and interesting biomarker, which is associated with the severity and poor outcome for patients. So here we compared 2 methods to detect NGEV. The current method with only CD15 and annexin 5 to label circulating NGEV without size exclusion chromatography washing, compared to the new combined method with the combination of the 3 selected antibodies, CD15, CD66B, and CD66C, with annexin 5 to label NGEV, with size exclusion chromatography washing. CD15 was chosen because extensive screening showed that is a detectable antibody specificity on NGEV. Indeed, based on extensive screening, CD15 labeling was selected as those generating the highest detection signal while preserving a good specificity. Under this condition, an increase of annexin 5 staining EV of plasmatic NGEV was detected when the new combined method was used, as illustrated on this graph. And this was confirmed in 10 sepsis patients. Furthermore, to evaluate the impact of the size exclusion chromatography washing on EV detection, platelet-derived EV were also measured using CD41 APC labeling and with or without size exclusion chromatography washing. The numeration of platelet EV were also significantly increased, as shown here. And what is very interesting is that the ratio between NGEV and platelet EV was significantly increased with the new combined method. This data indicates that the enrichment of NGEV in sepsis patients is not only due to the washing step, but also by the combination of the three selected antibodies. So finally, this results show that the association between antibody combination and size exclusion chromatography washing allow a better detection of NGEV in plasmatic samples. Additionally, the second element of the evaluation of the new combined method is to try to sort NGEV from COVID-19 patients. So here we compare three sort methods. The current method with only CG15 and annexin 5 to label NGEV without size exclusion chromatography washing. An intermediate method with the same labeling for NGEV with the use of the washing step by size exclusion chromatography. And the third method is a new combined method with the combination of the three selected antibodies and the size exclusion chromatography washing. So on this graph, you can see the labeling of circulating EV with neutrophil markers, CG15 alone or the combination of the three antibodies, and CG41 APC for platelets. So NGEV correspond to the events with P staining alone. So when the samples are not washed by size exclusion chromatography corresponding to the current strategy, it's almost impossible to sort NGEV from plasma. Then, after the use of size exclusion chromatography, the sorting of NGEV became possible, and the use of the antibody combination compared to the staining with CG15 alone allowed to significantly increase the sort of NGEV. So this data show that the sorting of NGEV was possible by the use of the new combined method, including washing sample with size exclusion chromatography and the combination of antibodies. It allowed to increase the brightness of NGEV compared to the background noise. So in conclusion, this work made it possible to obtain a more exhaustive marker list for NGEV detection by flow cytometry. And we showed that the use of size exclusion chromatography after labeling increased the detection of NGEV by decreasing the fluorescent background noise. And that the addition of several antibodies conjugated with the same fluorochrome combined with size exclusion chromatography washing allows a better detection of NGEV. This optimized method, this new combined method, drives to increase the detection of NGEV by flow cytometry in plasmatic samples and the possibility of considering the sort of circulating EV. This method needs to be validated in clinical trial, of course, to use NGEV as a clinical biomarker and apply to other subpopulations of circulating EV. To conclude, I would like to thank the C2VN and the MV team for help, and I would like to thank the Amuticid core facility and especially Stéphane Robert for his contribution. Thank you for your attention, and I'm listening to your questions.
Thanks so much, Amandine, for sharing your work. And so I'd like to invite you and Romaric both to participate here in the discussion. And just to remind everybody, if you have a question here, please put it into the chat box so that I can call on you. Let me just start with a few questions of my own. So one of those questions is, and I apologize if I missed this, but what would you estimate as the percentage of neutrophil-derived EVs versus the total EVs that you might find in the circulation? Can you estimate that?
Yes. So among the circulating EVs, the main subpopulation is platelet-derived EV, and neutrophil-derived EV represent a rare population. In the literature, it's very variable, the numeration of NGEV in plasmatic samples. Some study have no detection, and the most detected
yeah, something like as 10% or things like that as a maximum.
Okay. Yeah, 10% is the maximum. Okay. And I guess related to that, what sizes of vesicles are falling into the capabilities of your methods? So what would the size range be that you're looking at, do you think?
Yes, so by flow cytometry, we are not able to detect the events with the size lower than 150 nanometer, I think, around this this size. So of course, we don't have all the EVs detected by flow cytometry, but
Sure. Yeah, understood. And every method, right, has its own range of detection. So let's start out with Brian Dobosh. Please go ahead with your question on the channels.
Sure. Great talk and very cool paper and presentation. Can you just first clarify whether the CD15, 66B, and 66C were all in the same channels? Were they all the same PE?
Yes, it's exactly the same PE. It's really it's done to increase the fluorescence of each EV. It's done for that.
Yeah, is it okay if I ask a second question?
Yeah,
oh, sorry.
It's really the goal, yes. It's really the goal of this strategy to, because of the low antigen density of each antigen on this small EV, the strategy is really to try to combine a little bit more chance to catch a vesicle there. Of course, this will have a limitation. Of course, you cannot increase at probably more than 4 or 5 antibody for the small vesicles, because you will start to have some interaction between the antibody and not enough space to have more antibody. But at least for 3 or 4 antibodies, not a problem.
Just related to that, if it's okay, if I can ask another.
Yeah, please go ahead with your other question too.
Thanks, sorry. Well, you answered one of my steric hindrance ones, but for CD66C, I know that's expressed on epithelial cells and I believe endothelial cells as well. And I don't know if that was in your chart. Is there potential that we're seeing other EVs coming in and being contributed and being called neutrophil-derived EVs?
We did a large screening. It's not in the paper, but we have data on our different set of endothelial cells, and we never detect a signal for endothelial cell for CD66B or C. Yeah.
Okay. Yeah, I've never used, and we can talk later.
It's not in the paper. I don't think we include endothelial screening in the paper. That we have that in the lab, and we did like a parallel work with endothelial cells. To detect the best specificities, and we never detect a signal for these antibody on the endothelial cells. Yeah.
Okay, thanks. Yeah, I can shoot you guys an email afterwards. I've never really worked with endos at all, but I know for epithelial cells, at least a lot of ones we use, they have C on them.
Yeah, good to check.
But we can talk later. Thank you. Great talk.
Yeah. Interesting. Thanks for the contribution there. Amandine, did you want to add something?
No, thank you. It's perfect.
Right, yeah.
Thank you.
So it's interesting. I mean, we're all trying to find like the best markers, I'm sure, for these cells, and it's important to take into consideration too whether, even if something is expressed on the cell, whether it's actually also released on the EVs, because in some cases that can also change our approach. So good points there. We next have a question from Zheng Zhao. Please go ahead.
Yeah, hello, this is Zheng. So can you hear me clearly?
We can, yes.
Okay, thank you. For the particle size analysis, you mentioned you use the resist pulse sensing. So could you let me know what is the instrument you use for those?
Yes, it's a Q-nano instrument from Eisen.
Okay, thank you.
Okay.
Very good. All right. Thank you so much. And then next we have a few questions actually from Xin Zhang. If you'd like to, you're welcome to ask both of your questions here.
So very nice talk and very interesting result, and actually not supported from our study. So then we are very excited to hear your presentation. So then as I wrote in the box in the chat, so then I have two questions. Number one, we use the SBI SEC kit, and then we found actually somehow we see much lower positive signal after the SEC process. So, and we haven't know if it's due to the removing the is due to the affecting the antibody binding, or it's just because dismiss the fluorescence intensity. So that's why I'm asking if you guys have ever tested if this kind of process. I know you did that after the staining. So my question is if it's due to removing the free antibody, or it's just because the buffer dismiss the fluorescence. So then you see the decreased fluorescence intensity after SEC wash step.
Yes, I think it could be due to the removal of free antibody and free fluorochrome also that could decrease the median fluorescence intensity. I think it's possible, but
yeah, just to complement that, to add something is what is interesting in maybe it's really visible in the paper. In our hand, I don't know if it's because of the buffer or not, but we did not see a decrease of the mean fluorescence intensity for the EV event, for the annexin 5 positive and neutrophil antigen positive events. We did not see a decrease of that. We see only the decrease for the background noise. For the negative event for annexin 5 or negative for the specific neutrophil antigens, we see the decrease, and we count more vesicle because we see we discriminate smaller intensity of fluorescence, but we have not observed a decrease in the mean fluorescence intensity of the clearly visible events. I don't know if it's you ask about a buffer. Maybe that may impact the cytosol chromatography.
Yeah,
it's good to check.
Yeah, I think it could be interesting to look at either nanotracker analysis or transmission microscopy to see like before and after the SEC step, if you see the decrease in the number of those kind of class of the free antibodies, or is remain the same. So this is just my comments.
Yeah. Can I ask you a question back? When you observe this decrease of fluorescence intensity, or you say maybe a removal of or dismissing of the fluorescence, which fluorochrome you observe that?
We see several ones, like for example, like PE and PECY 5.5. Not every fluorescence affected by SEC, but some of them dramatically affected.
Is it more intense for tandem fluorochromes, or it's also observed similarly for fluorochrome that are not tandems?
I think we see the decrease both percentage and the intensity both, but the intensity not changed too much, but mainly the percentage, like they dramatic decrease, like from 20% decrease to 5%. It's not complete gone. It still have population over there. That means still we see the binding, but the percentage dramatic decrease. Yeah, so it's just something to share with you, so it can be you can consider in your future study. And then another question is about the size. Like we see like both in human and mice, we see the annexin 5 signal is much higher in the large size EVs than the small size EVs. So then I do not know if you guys also see the expression of Alexin-5 related to size.
I'm not sure I totally understand. It's about
the intensity of annexin-5 on the larger vesicle. I think clearly, yes, we observe that.
Yes,
So
yes.
it's clearly that in relation to the volume of the events, clearly there is more annexin-5, and clearly the largest vesicle more easily also expresses the phosphatidylserine than the smallest. And it's mainly among the smallest that we have various populations. Some of them, without freezing, have no expression of anionic phospholipid, or at least there are no binding with annexin-5. But the more you look at the biggest vesicles, not necessarily above one micrometers, but even smaller. And in this subset of vesicles, the largest one, the large majority of the vesicle, even without freezing, clearly express the anionic phospholipid.
Okay, great, thank you.
It was the debate before the story of joining the exosome world and the microparticle world. It was a big debate because, you know, at the beginning, the microparticles, so the large EVs or a part of the large EVs, were initially defined as an annexin-5 positive event. Or,
exactly.
After that, in the story, there were debate because we observe also negative event for that. And it was more clearly visible when we decrease the sensitivity, improve the sensitivity, and look at smaller events. And there clearly you have all the categories of vesicle that are able to be released by the cell without a flip-flop mechanisms, or and clearly, yes, in the smaller world, you have this kind of vesicle without anionic phospholipid. But for the biggest events, either the apoptotic bodies or the large EVs, clearly most of the events are positive for the anionic phospholipid.
Yeah, great, thank you. So I think we see the similar findings. We also see like Alexin-5 in the small EVs that is different from many of the original thinking in the literature. So I'm glad to see the similar result from your guys. Yeah, thank you. Very nice presentation, very nice work.
Well, thanks so much for the questions. And at the risk of taking us on a tangent here, Romaric, it's so fascinating to think about the history of EV research and how, you know, you did have this distinction between the microparticle research, which was largely driven by flow cytometry, and then the exosome research, which was in large part because of the capabilities of electron microscopy.
Yeah.
And so you had these, you know, these two almost completely distinct efforts that were going on, looking at the, you know, the multivesicular body kind of biology, but then also at what was happening in the blood with release from blood cell types with the larger particles. So along the way, you know, if we're talking about phosphatidylserine exposure, and you know that whole debate that went on much better than I do. But in the cell, you know, there are the flipases that are flipping the phosphatidylserine back to the inner leaflet when they flip out. And theoretically, you could have those same flipases on the EVs, especially the larger the EV, the more likely you would have a flipase that would be there. However, it's going to be energy dependent. So my question for you is just what your thoughts are on that possibility of flipping the phosphatidylserine back in if it happens, you know, it happens to flip out on the EV membrane, and whether that's going to be dependent on the age of the EV, like how long it has been since the EV has been released, and has it been able to deplete any, you know, energy stores that it actually had inside it.
Yeah, what you say is very interesting, because it's very possible that these happen. I don't know if you have data on that, on the time or kinetics with an internalization or of the anionic phospholipid. what is clear is depending on the buffer, depending on, of course, because all that is calcium dependent, depending on the cycle of freeze-thaw cycle, of course, you clearly modify these flip-flop mechanisms and what happened. That's why I say, yes, when you freeze large EVs, clearly, or when you thaw that, really almost 100% of them express now the anionic phospholipid, which is not necessarily the case, or at maybe lower intensity when you have only the fresh sample coming from jacket blood or another. So yes, I think what you say is really possible, and it will be interesting to have really clear data on I don't know, a back phenomenon or a reverse phenomenon concerning especially if we use that as a detection marker or a biomarker, an impact on the pre-analytical condition before measurement in patients, for example.
Yeah, I think there's still a lot to learn there, and it has tremendous implications for something like the half-life of the EV in circulation. So we still don't know a lot about the half-lives of EVs that have come from these different cell types. And endogenously, I'm saying, like most of our pharmacokinetics stuff has come from exogenously introduced EVs.
Exactly, this injection of
yeah, and you know, the phosphatidylserine, I think the exposure of PS is also going to be important in helping to determine how long the EV sticks around and where it goes.
Yeah, of course. Basically, in classical cell biology, it's just a eat me marker. So
yeah,
of course, it's important for that. Yeah.
Yeah, indeed. So, and that actually leads me into the other another question that I had, and that was on, you know, recently there have been a lot of labs that have started looking at or trying to look at EVs in tissues. So and blood is also a tissue, but in a solid tissue, for example. So, and of course, neutrophils are going into tissues and responding to inflammatory events there. Do you think that your method would also be useful in obtaining EVs from a tissue preparation?
Yes, it could be possible. For the sorting, you mean, for example?
Yes.
I think it could be great to try this strategy with using a solid tissue and to sort NGV from tissue. Yes, it could be great to test that.
Yeah, I think it would be really cool to try.
Yeah, if we can dissociate the tissue, it's okay.
Yes, that's the key, dissociating the tissue in a way that does not create a bunch of artifacts, right? So that's the challenge. So so we also have a question here from Tanina Arab. Tanina, please go ahead.
Hey everyone. Hi Amandine, very nice talk. I think my question joined a little bit the previous one from Xingzang, where basically I was just wondering, since what I understood from your presentation is that you have these EVs that are isolated or purified, then you complex or you label them with an antibody, and then you wanted to remove these extra antibodies using size exclusion chromatography. So I was wondering if the decrease that you have been seeing in the fluorescence is actually due to the loss of the specific bindings, or also the loss of EVs in your matrix of size exclusion chromatography, because it's a very pure sample and less complex. So that may happen as well because of the stickiness of EVs. But I think it was extensively discussed with Xingzang, and she kind of suggested experiment to check that actually this step is efficient, and also you're actually only removing the antibodies and not part of your particles. So I don't really have a follow-up, I guess, unless you want to add any details.
Yes, of course, the EV are not totally recovered at the end of size exclusion chromatography, but this loss of EV did not impact the median fluorescence intensity of the EV.
Not impact the median, okay.
Yes,
okay.
Because of course we lost a little part of EV during the size exclusion chromatography because it's not a yield of 100%, but this loss did not impact the median fluorescence intensity of the population analyzed after by flow cytometry.
Exactly, and what we want to conclude from that is that the detectability of each EV is not impacted. Of course, you may lose, as a quantitative analysis, you may lose a fraction of the EV, but for each EV, you maintain the same detectability.
Okay, you mean the percentage of the markers that is present?
You may lose 20 or 20% of your EV, but it's not decreasing the detectability by fluorescence. You lost them because they stick or because the SEC has not an 100% recovery. For that implies a new question: how I can make a clinical study with that? Because how can I standardize this loss of 10, 20%, 15% that may vary according to the patients. So here we may have a suggestion to use the annexin 5 labeling that is done after the SEC colon as a standardization factor. So you may say, I count the absolute number of annexin 5 events, and then I deduce, I normalize the loss of EVs with this, the measurement of annexin 5. So
are you sure that,
you can make a correction of your loss using the annexin 5 labeling that you can check before and after the SEC colon, for example.
I see your point. Okay, thank you so much.
But yes, it's of course the issue with the SEC that you never maintain perfectly 100% of recovery, at least with the buffer and the colon we are using so far.
Yeah, thank you.
Very good. All right. Well, it looks like we have come to the end of the questions that are in the chat box. So unless anybody has a last minute question here for Amandine and Romaric, we will probably end for today. Any last words from our speakers, our guests here today?
So just a last word from me.
Yes,
Thank
please.
you very much for the invitation. It's a great pleasure to present my work. Thank you again.
Well, thank you. Thank you for joining, and congratulations on publishing this in JEV, and best of luck for the continuing work and with your ongoing career. So thank you both for joining today. Thank you everybody for being part of the EV Club. And please reach out if you have anything that you'd like to share on EV Club. If you see a great paper that you'd like to present here, we do have some slots coming up in the new year, 2023. Hard to believe. But please feel free to reach out to me and we'll get you scheduled. So thanks again and take care, everyone. Have a good rest of the week.
Thank you. Bye.